In this video, we're going to go over the Lab 6 data analysis. Walking gait, economics, shod versus barefoot. Shod just means to be shoed, or to wear shoes, or to wear something on your feet, essentially, versus unshod or barefoot in this case. Shod gets used in the literature, so that's why I have it here. So a little bit about this. This will be our penultimate lab to close out the summer 2026, at least when I'm recording this. May get used in the future as well, I hope it does. And we'll be going through and working through things like impulse, velocity, center of mass velocity, power work, and getting a lot of variables from that. And hopefully being able to connect this from our applied gait economics for walking that I have in lecture, all the way through to connecting it to exercise physiology, some things in exercise physiology, metabolic things in exercise physiology, as you'll be able to see over here. We'll be connecting it to horizontal VO2. We'll be getting to that. So there will be a lot of things. I'm going to try to keep this video short. You can see it on your screen, but I can't because I haven't recorded it entirely yet. So make sure you have the combined Excels pulled up. It has two sheets to it, shod walk, barefoot walk. There's a video, it's also on the assignment page with this, that goes over or displays me collecting this actual data. And it also has run in there. I wasn't possibly going to include running, but I chose not to. It's going to be too much. We already have plenty here. We have plenty here, so we'll just do these two for walking. So, without further ado, make sure you have this pulled up, and let's get started with our calculations. So, for shod walk, that's what I'm going to do first. We need to do the impulse. Let's do the area of the curve. So, equals 2. We're going to start with finding the midpoint of force. Midpoint of force, you do the one that's within the row. Previous one, sum those together and divide by 2. And then multiply by the change in time, which is 0.001. Now you may be wondering, oh, don't you have to subtract by body weight or anything like that? Not for this one, thankfully, because we're using the horizontal force. If we were doing the vertical force, we would, but since we're doing horizontal force, we're not under the influence of a gravitational force resisting us in that horizontal direction, so we don't need to, which is nice. Then we can just hit the down button. Great. And then center of mass velocity. So to get this one, we're going to take the impulse, divide it by mass, and add in the previous velocity, or our current velocity that we were at in the step beforehand. So equals 2, point it towards the impulse in that same row. We'll divide by mass. Make sure you write the correct mass here. Since we're doing the shod one, I weigh just a little bit more, or I have a little bit more mass. So 80.548, and then add in that previous velocity. Okay. That's looking good. It's going down, 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 down. And actually, looks like I kept it in here already. That's okay. Looks like it turns around right there and starts being propulsive there. Cool. Power. Power, I think I already have it here, but it's force times velocity. Easy enough. And then work. Here we need to do the area of the curve of power. So equals 2. And then power is going to be the midpoint, just like it was for impulse. The midpoint, divide by 2. And then times the time difference, which is 0.001. Excellent. Goes down. I'm going to skip to once it goes from eccentric to concentric. Great. Excellent. So that's all of those calculations, now we can figure out all of our smaller calculations here across, which is just going to go, some of it's going to be for this table, and then the other parts are going to be to complete everything down below here. Okay, so net impulse, we'll just take the sum of impulse excellent. So right here I'm off the force plate after this one, so I'm going to stop there. Okay, so net impulse is just, for the shod condition, is just slightly above 0, which means there'd be the tiniest increase in velocity over that entire step cycle. It should not increase that much, or it shouldn't be much larger. There is another piece I am missing, is not, I don't have my other foot that did not contact the force plate, which would be resisting for a very small period of time too. Another force plate, the other force plate. But again, if I get just the slightest positive here, that is fine. But we don't want it rather large, because that would show that I was accelerating really hard or trying to push myself really hard to go faster in that step while I'm going through that step cycle. Okay, then work, braking. This will be the sum in the work. We're going to go up until we hit eccentric. Okay. And then propulsive equal to sum. I'm going to use this to skip on down. All right. Cool. Braking time. So this minus the start when we first contact the force plate. Propulsive time. Let's go to the end right before I leave the force plate. And subtract that from just after eccentric, concentric. Okay, looks like propulsive time's a little bit less than the braking time. And then propulsive work was just a little bit more than the braking work as well. So work mechanical, this one's just going to be the sum of work propulsive plus work braking. So about 0.5, not bad. 0.5 joules. Again, it should be very close to 0 done by each. We don't want a large amount of mechanical work change, because that would mean I was either inputting a whole bunch of chemical energy to increase my step rate, or increase my work done during that step to increase horizontal acceleration. Okay, this is the propulsive to brake ratio. We're just going to take the propulsive time divided by braking time. The step rate. This one's going to be, we'll take 1 divided by the sum of the two, of the braking time and propulsive time. So braking time plus propulsive time. And this is going to be steps per second, so about 1.387 steps per second. And then step length. This will be equals to 1.3. 1.3 was meters per second that, again, I was about walking at as best as I could tell and tried to control for as much as I could, divided by step rate. Okay, and that tells me how long each step was. So step would be the heel of my right foot to the heel of my left foot when it lands, and not how far my right foot goes between strides of it contacting and then contacting the force plate again or the ground again, but how long each step was or is about 0.937 meters per step in shoes or in the shod condition. Then we have work for metabolic. Work metabolic. This one's going to take just a little bit more. So, what's kind of cool about this is we have both the propulsive and braking work. With those, we're going to assume a 25% efficiency in concentric propulsive and 120% eccentric muscle efficiency in the braking, which come from other studies that have been done. And using those, we can get about how much chemical energy in joules was used, or metabolic energy was used in joules. So we're going to do equals to, we'll point to the propulsive work divided by 0.25, and then add to that the braking, and divide that by minus 1.2. If you want to put in the 0, you can. It doesn't matter because it's 0 in this case. And we get 192.6 joules. 192.6 joules. Then we'll do power. Metabolic. That's going to be the work divided by the time of that step. So equals to this divided by braking time plus propulsive time. So about 267 watts, or joules per second. Now, cost of transport. This was one of our penultimate things that we talked about in lecture, in the walking lecture especially, and also the running lecture, but specifically for the walking here. We'll need to take the power metabolic and divide it by 1.3. 1.3 is our meters per second approximate forward center of mass velocity we are maintaining, and divide that by body mass. So equals to power meta divided by 1.3 times body weight, and let's just make sure we got it correct, 80.548. So about 2.552 joules per kilogram per meter. So not too bad overall. Now let's go ahead and convert this to horizontal VO2. Horizontal VO2, we're going to go from joules to milliliters of O2 using 20.92. And then we also need to convert this from meters into minute. Per meter to per minute. So let's go ahead and do equals to 78 times cost of transport metabolic divided by 20.92. Okay, so about 9.515 milliliters per kilogram body weight per minute. And that's only in the horizontal. This one does not include things such as the mechanical work of me raising my center of mass up, because it does take work for me to raise my center of mass or change it to go up, because I have to provide force vertical for it to go up. Does not include other metabolic components such as resting VO2 or internal work done by the muscles themselves, things like that. This is how much energy am I using to move my center of mass. Alright, so that completes one of these, and you can see all these zeros here. At least mine shows 0 here. Yours probably will at this point. But these are just pointing to the barefoot, and this is just more for later, so it's easier to look at all of these things at once. So let's go ahead and do the same thing for the barefoot condition. So barefoot, we'll need to do impulse again. So equals to, find the midpoint, and multiply by the change in time. Velocity, we just need to take impulse, divide it by mass. In this case, it was 79.9 if I remember correct. Yes. And then add previous velocity. Excellent. Power. Let's see, I might have done this. No, I didn't do it here. That's okay. So equals to force times current velocity. Current force times current velocity. And work equals to finding the midpoint multiplying by the change in time. Excellent. So now let's go ahead and do net impulse equal to sum we'll stop right where I'm last contacting the force plate. Okay, so a little bit more impulse here. Just a little bit more. I think the previous one was 0.3-ish or so. 3 Newton meters. 0.3 Newton meters per Newton meters second. Sorry, Newton seconds. Newton seconds, not Newton meters. Okay, work breaking. Sum. We'll go work right up to, I already did it on the way down before. So let's go right to there. And then sum for the propulsive. Where I'm last contacting. Cool. So I can tell there's already a little bit more of a difference here. A little bit more propulsive on that step. So what was that braking time? Let's check this out. So the time of braking, because I used this negative here, I'm going to start here to where I first contact the plate. And then propulsive time. I'm going to go to where I last contact the force plate, which is right here, to where I change from that negative to positive again. So interesting, a little bit more propulsive time here versus the braking time, whereas it was opposite for the shoe. So work mechanical, net work mechanical. That's just the sum of the work. So I had 0.5 before, and this one was 1.5. Still pretty close to 0, but it's a little bit more. Might have had just a little bit more propulsive, a little bit more propulsion forward overall. That propulsion to brake ratio of time. So propulsive time divided by braking time. So yeah, the previous one was below 0. This one's a little bit above, a little bit below 1. This one's a little bit above 1. Step rate. Here, we'll take 1 divided by the propulsive time plus braking time. Make sure that's within these parentheses. So if I remember right, it was about 1.3, and this one's about 1.7, so I'm stepping a little bit faster. A little bit faster stepping. Let's see about length of a step. 1.3 divided by step rate. So 0.733. That's a little bit shorter step with a little bit faster rate, it looks like, from memory. And then work metabolic. Again, here we have that 0.25 and negative 1.2 that we need to use. So equals to the propulsive work divided by 0.25 plus braking divided by negative 1.2. I'll put the 0 in there for completeness, although it gets rid of it, as you can see. Excellent. So this one, interesting. 161.87. That's a little bit less. I think the other was 192 or so. So it looks like there's just a little bit less metabolic work that was done on this step, or stepping with barefoot. let's see how that pans out. Although we had a faster step rate and shorter step length. So how do these gait mechanic changes work with all that? Let's see how all this pans out. So power. So power was metabolic work divided by our time of that step. And I know I didn't mention it before, but this braking time and propulsive time are much shorter than they were for the shod condition, so that makes a lot of sense. So work metabolic divided by the time of that step. So 287. All right. Then cost of transport. Metabolic, we need to take the power divided by, let's put parentheses, 1.3 times mass, and the mass was 79.9. Don't use the one for the barefoot because that, don't use the one for the shoes with the one for the barefoot because that's not correct. All right, cost of transport. I believe the other was 2.55 and this one's 2.76. So a little bit higher cost of transport. Now let's see how that pans out for horizontal VO2. Equals to 78 times cost of transport divided by 20.92. So 10.302. Let's go ahead and look over here. Here, now we can easily look at how all of these things pan out across. So cost of transport, a little bit more for the barefoot condition compared to the shoe, even though the work metabolic was a little bit less. And that's because the person has to walk at a faster step rate and their step length is less to maintain that same velocity. Or at least for me, I had to do that. And if you look back at the video, you can see I do actually have a shorter stride with bare feet versus shoes. And all of that turns out to be, at least in the horizontal, about let's just take a look at the difference. You don't have to do it on here, but what is that difference? About 0.7 or about 0.8 milliliters per kilogram of body weight per minute. That doesn't sound like much, but it is. It does matter in races especially. It matters in whatever you're doing that's where you're trying to minimize energy. And it looks like, from our data, that shoes minimize that energy. We can't look at total energy overall because we don't have a full center of mass 3D motion capture setup going where we can track energy overall of it. Then we'd be able to look at things like energy recovery per step and a whole bunch of other things, which would be nice, but it's too complicated for this setup. You can see there's a little bit more braking because I'm probably taking I am taking those steps that are a little bit further out, but I'm also getting that propulsive. I'm getting a lot of that back with the propulsive because I'm not having to put in as much chemical energy overall to maintain my mechanical energy going forward mechanical energy or forward center of mass velocity. It's all about how much chemical energy am I having to put in to maintain that walking speed. Now again, that 1.3 is about as close as I can come between the two, and it's pretty dead on. It's pretty close just using video and known distance of how far I walked. It's not exact. It'd be better if I had the full 3D motion capture setup, but that's close enough and decent enough for what we're doing here. If anything, the shoe condition is walking just maybe the slightest bit faster. It's still very, very close. It's maybe at least about 0.1 off or so. All right, let's do our last thing, which could have been one of our first things we did. Let's create some scatter plots. I think this will tell the tail a little bit better. So I was holding Control Command or Control Shift to do that. This may not work as well on Google Sheets if you're doing it on there. This works much better on Excel, and that's why I like Excel a little bit better. Let's do Insert, Scatter Plot. Excellent. And actually I'm going to change this to 1. And this one is the shod? Okay. Vertical and horizontal ground reaction force. And let's do the same thing for barefoot. Awesome. And we'll just copy it as well over here. All right, so I did mine intentionally to put 1 at the end and starting from 0 so that you can see this one, the shod one, or the shoe one, is very smooth in comparison, whereas the barefoot one, my heel hit here and then my foot had to slap down pretty much immediately because I don't want to maintain as much weight of my weight on my calcaneus. So I just slap that down pretty quickly. And again, because my steps have to be faster with a shorter stride length, or step length, because my steps have to be, or are shorter with a faster step length, my contact time is going to be less. So it's easy to just tell from these graphs, oh, about 0.7 versus 0.5 something. So I was taking faster steps even though I had very close to the exact same center of mass walking speed, even though, as I said, if you look at the exact times or try to time it up very much exactly using video, the shod's actually just a hair faster overall. Just, as I said, about 0.1. It's as close as I can maintain by myself just walking with all this stuff going around. Again. Okay, otherwise, you can just copy and paste all of this stuff into here, into the appropriate places. You have a little bit of interpretation to do throughout this, but I think you'll get a lot out of it. We're, again, connecting from what we've learned in biomechanics all the way through to what you will or have learned if you've taken it in exercise physiology. So we're just kind of connecting a nice through line of mechanical energy, maintaining mechanical energy, to minimizing metabolic energy. Anyways, if you have any questions, please feel free to reach out. Otherwise, thanks for watching.